All right, section 7.4 talks about a few more tools that we can use to help us solve for these differential equations, either going into the Laplace world or coming back to the real world. And then we're going to get introduced to another concept. We're studying, this class is about differential equations. Do you guys remember what the definition of differential equations is? What is a differential equation? A what? An equation that contains a derivative of a function that you're trying to solve for. So yeah, essentially an equation that has derivatives. And so we're going to also take a look at an equation that might contain an integral instead of a derivative. And so that's coming up in this section. And then at the very end of today, we should be able to touch on the next section, which is going to talk about a special type of function. Lost my pen. All right, operational properties. So here is another property that we can use to take advantage of to make our transformations from the real world to the Laplace world a little bit easier. If we have t to the n power times another function and we want to take that to the Laplace world, then we can simply multiply or simply take the derivative of the actual function and multiply it by -1 to the n. So that's an interesting concept, interesting idea. And these ideas really, if you want to get a full appreciation for them, you should try to prove it using the definition of the Laplace transform, which is that infinite integral from 0 to infinity and stuff. So we're not going to do that, but we will use the facts that come out of that and see if it'll be helpful for any of the things that we do. So let's do an example for this. We have number one, looks like a nice simple example to start off with. We want the Laplace transform of t times e to the -10t. And so to use this function or to use this formula, what we want to do is we want to identify the n that we're using, and then we want to identify the function that we're going to actually take the transform of, and then see how that fits into the formula. So according to the formula, this thing should equal to -1 to the first power times the first derivative with respect to the s variable, right? We're working in the Laplace world. The first derivative of the transform of this function. So the transform of that function, that would be capital F, this is e to the something, so it's 1 over s minus 10. And so we simply take the derivative of that. So s minus 10, the chain rule, s minus 10 to the negative first power would be s minus 10 to the -2 power times -1 or something like that, times the derivative of the inside, which is just 1. So I think this is going to be just the regular 1 over s minus 10 squared. No. I mean, we could, since we are skipping a whole chapter. But, well, it's replacing this whole thing, t to the n times f of t. Put that into your function, yeah. Bob, do something. We could work it out. Like I said, I encourage you to go through the proof of that in your own time, and then get that personal satisfaction of saying, hey, this is kind of cool. And then you would get more appreciation for actually using this instead of just abusing it like physics people do. Anyways, sorry, Attila. Let's take a look at one of these things that's square. Let's do number 6. So we want the Laplace transform of t squared cosine of t, and we have n is equal to 2. Yeah. Yeah. Right. Yeah. This is just an alternate method. Yeah. For anything you want to do, you can always go back and use the definition of the Laplace transform to make your transformation. But the idea is that if you have that table and a bunch of these other operational properties that we're talking about, then why bother, right? Yeah. So yeah, these integrals get a lot more complicated if you try to do it by the definition. No. You could go through it. I mean, especially if you're a math major, you should go through it and then I, yeah, you should do it. You people who are going to be math or even theoretical physics people, engineers really don't care about the proofs. They just use and abuse. All right, over here we're looking at n is equal to 2 in this case, and our function is cosine of t. According to that table that Delilah put up there for us, is I didn't even check if it was right. It's right, right? So the cosine is that so the variable here is 1, or the coefficient of the angle is 1, so it'll be s divided by s squared plus 1. So we have -1 raised to the second power, so that's going to be positive. And then we want the second derivative of the transformation of cosine. Transformation of cosine, like I said, is s over s squared plus 1. So we need to do 2 derivatives here. Ooh. Can you guys just do it? All right. Product rule or chain rule or quotient, whatever, a couple of times. Derivative of the first. So let's do this. Say we're working on the side. We have low d high. So low s squared plus 1. D high is 1 minus high s d low 2s divided by low squared. And so we obviously want to simplify this before doing another derivative. So we have s squared minus plus 1 and then minus 2s squared. So that would be negative. So negative s squared plus 1 divided by s squared plus 1 squared. I don't think that cancels, so let's take the derivative again. So ds again. So low s squared plus 1 squared d high minus 2s minus high minus s squared plus 1 d low. Ooh. So 2s squared plus 1 to the first power times 2s all over low squared, s squared plus 1 the fourth power. All right, again, we want to simplify this as much as we can. Actually, we don't have to because, you know, we don't have to. So let's just leave it like that. Actually, let's make some attempt. Let's pretend that we care, and then simplify this a little bit. I see an s plus 1 that's common to both terms. I essentially have two terms here, right? The second term just looks like it's a lot more complicated, but I have an s squared plus 1. So let me get rid of one of those s squared plus 1s with one of these s squared plus 1s in the denominator. Yeah. This has a minus s squared plus 1. I should have written it as 1 minus s squared, but I kept it like that. Anyways. So anyways, I think there's just an s squared plus 1 gone. So this will be to the third power after we cancel out one of these and one of these. So that would leave us with a s squared plus 1 times negative 2s minus negative s squared plus 1 times 4s over s squared plus 1 to the third power. All right. I don't know about pretty, but it's a little simpler. And I bet if we multiply things out, we could simplify it even nicer. So we have, is this a minus? This is a minus. So this is a minus 2s cubed minus 2s. And then here, let's go ahead and multiply this. Negative, negative is a positive. So that's positive 4s cubed. And then a negative 4s. So we got some terms to work itself out and simplify a little bit and divide this by s squared plus 1 cubed. So we have 2s cubed minus 6s all over s squared plus 1 to the third. And I don't think we can simplify this anymore. We could factor out maybe a 2s in the numerator if that helps us with whatever it is we're dealing with. But anyways, we're just going to the Laplace world, and so here's our simplified version. Okay. So that's a few examples or a couple of examples of this particular operational property. And I think this is mostly useful going from the real world to the Laplace world when you're transforming, in case you have any t's multiplied by some function. All right, let's move on. The next idea is a convolution. This is, I think we didn't really talk about this, but some people have alluded to this idea. That might come into play. So the convolution is the symbol that we will use. This is a convolution that happens in the real world. And what happens is that you take this convolution, it's defined by this integral, and then you put that into the Laplace world. And then what happens in the Laplace world is kind of interesting. So this is a convolution definition. So there's a warning down here that this says it's not multiplication. You're not doing a multiplication here. This is formally a convolution. A convolution is defined to be an integral from 0 to t of f of some variable times g of t minus that variable, d that variable. So in this case, we're using the variable tau. Other books you might look at might have a different variable associated with it. But this would allow us, more importantly, allows us to take a look at theorem number, I guess number 2, 7.4.2. That says the Laplace transform of a convolution is actually equal to the product of Laplace transforms in the Laplace world. So the Laplace transform of a convolution is equal to the product of the Laplace transforms in the Laplace world. Okay, so getting that product is an interesting and important thing for us. Yeah. Yes. It turns out that this also commutes. I don't think I put that here, but if you switch the order of f and g, then in the convolution, then you switch the order of f and g in the multiplication, which is equal. Yes. So this is commutative, and it's not multiplication in the real world. It's convolution in the real world, multiplication in the Laplace world. So in some cases, this is probably going to be more important for us when we're transforming back from the Laplace world. If we see something that looks like it's a product of two things, how does that look like in the real world? I don't know if I have any examples of going into the Laplace world. Yeah, I don't know. We'll see if we can use this as we do some examples of actually transforming or translating. Spring? Oh, like the spring things? Oh, well, let's just do a differential equation, see what happens. So let's pick a differential equation problem from this section and see if we can use any of these properties. Okay. Let's see. I don't know. Let's try number 11. Second order. I don't know if we should do a second order yet. Oh well, let's try it. So here we have the second order differential equation. It's y double prime plus 9y is equal to cosine 3t. And we have initial conditions, y of 0 is equal to 2, and y prime of 0 is equal to 5. All right. So we need to do our transformations. So we do a Laplace transformation, and we'll just do it term by term because the Laplace is linear. We have s squared, capital Y of s, minus s times, is this y or y prime? Y. 0 minus y prime of 0. So that's the double prime, and then 9y, that's just y of s, is equal to, now we have cosine 3t. So that's another transformation. It'll be s divided by s squared plus 3 squared. Okay. So now we're in the Laplace world. Let's just do some algebra. Well, let's plug in some information first. We have a 2 and we have a 5. And so what do we have now? I'm going to start collecting the y, capital Y's together. minus 2s minus 5 is equal to s over s squared plus 9. Now let's bring the 2s. All these examples seem to have 5s in them. Let's bring the 2s plus 5 on the other side. And then let's divide by 9, or s squared plus 9. So y of s is equal to s over s squared plus 9. Oh, this is going to be squared, right? Plus 2s plus 5 divided by s squared plus 9. Suppose we should try to combine everything. So this is the algebra part. So this is the easy part, right? This is the whole reason why we go to the Laplace world, because we're exchanging our calculus work for algebra work, and this is the algebra work. So the other hard part is going back, see if we can bring this back to the real world. And what we need to do is we need to make it look like one of those formulas, or be able to take advantage of some of the rules, properties that we just learning. So I think if we combine this into one fraction, that's usually one of the key things to do. Combine it into one fraction, then that might help. So common denominator. What? Then let's multiply this out, and I guess I should keep my old other pen color. Let's multiply this out. This is what is it? 2s cubed plus 5s squared plus 18s plus 45. And then we have an s here that we can combine, and so we can write all the stuff into one big fraction. Okay, so the 18s and then the one extra s, that makes a 19s. So our numerator is going to be 2s cubed plus 5s squared plus 18 plus 1 is 19s plus 45 is equal to s squared plus 9 quantity squared. Well, you could try it. You could try it now or later, see how it compares to this. It might be easier. Well, you think on your own and see. Oh yeah, I guess so. We could do that. The 2s plus 5 can split into sine and cosine, and then we can deal with the other one separately. You want to do that? I'm sorry, Michael made a more convincing argument. We'll do what you're saying, except I'm doing it because he said so. Nothing. Yeah, that's a good idea. Okay. 2s over s squared plus 9 plus 5 over s squared plus 9. Geez, these 5s and s's. All right, so yeah, it looks like we got a sine and cosine for the last two terms. Let's take a look at the first term and see how we could deal with that. Does that look like something? I don't know. It could look like, well, we could do one of two things. First of all, if you look at it really carefully, um, is it a derivative of something? So I guess there's two ways to look at it, and we can choose one of the two properties that we just learned. Um, one way to approach this, one way to approach this and say is to say that this could be s divided by s squared plus 9 times 1 over s squared plus 9. And in that case, it looks like it kind of looks like this would be f of s and g of s, right? That's one approach, and then we can come back and do the convolution theorem. The other approach, I'll put it on the other side. The other approach is to take a look at this and say, hey, this looks like a derivative of something, doesn't it? Yeah, so this looks like it might be the derivative of 1 over s squared plus 9 with some multiple of something that I'm going to put alpha, like 1/2 or negative 1/2. So I'll put alpha there for now, but it looks like this is the derivative of that, right? So this is the, what did they call that? Derivative of transformation. Derivative of transformation. So we could take either approach. I think this convolution approach might be a little bit more difficult because we'd have to do an integral. Um, this one, we just have to figure out what that alpha is and then backtrack. So maybe we can, I'll do it one way and you do it another way in your own time. Josh. Uh, yeah, so the derivative is a little bit more, less, it's a little bit less intuitive because you have to actually be thinking about derivatives in advance. And the way I thought about this is that I got an s squared plus 9 quantity squared. So that looks like it's a derivative of 1 over s squared plus 9, because when you take the derivative, you raise the power in the denominator. But the thing to worry about is that there's an s on top. So the s on top is telling me that, oh, there's probably the chain rule that's happening here, and the derivative of s squared is 2s. So there's that extra s popping out. So the doing it this way or identifying it this way, I think it's a lot more difficult to do because it's less intuitive. But it's one of those things where you'll see s squared plus k squared to the second power to the third power a bunch of times, and so you'll after doing several of these, this whole idea about being able to identify these derivative transformations might be a little bit easier, but it's not obvious when you first look at it. So it's something that you just have to get used to. Um, well, technically, we did the algebra already. It's the bridging back to go back to the Lapuz world. That's that's going to involve calculus. Go back to the real world. Yeah, sorry. Thanks. All right, so I think this is it. If we take the derivative of this, it's going to be s squared plus 9 to the negative 2 power, or negative 1, s squared plus 9 to the negative 2 times 2s. And this is where, if you start piecing this together, there's a negative 1/2 s over s squared plus 9 quantity squared. And that's that alpha that we would be looking for. It looks like there's an s squared involved. So let's take advantage of that, use this, and then at home, I encourage you to find the integral from 0 to t of the sine and cosine shift and stuff like that. least I'm on record saying I encourage you to do that, right? And then whatever you do is on your own. All right. So how do we bring this back? Um, so maybe I'll just put that there's a 1/2. Let's get everything all prepped up to make it look nice and ready. There's a negative 1/2. Oops, let me write it this way. So I don't want to change the form of this thing. But I want the form to be negative 1/2 s over s squared plus 9 quantity squared. And so I'll multiply this by a negative 2 on the outside. So when it's all said and done, it's back to the original form, right? But before I do the Laplace, I want this to take it back to the real world. So this is equal to these two things are equal, right? This thing that I just wrote in the first term. All right. So now this one, there's already an s, so I'll just do the 2 and then s over s squared plus 9. And the things that are in brackets are things that I want that's readily transformed back into the real world. And so any constants I need to mess around with, I'll just mess around with it and then put it outside. Like this last one, I want to have a 3 up on top, right? Because 9 is equal to 3 squared. But then there's that 5. And then now if I multiply this by 3, I have to divide by 3 to keep it equal. So I will have an extra 5/3 sticking out there. So by taking care of those constants, I have now written my function in the Laplace world ready to take back to the real world. So this is our stack. Green. So this is going to go to the real world, and then we will get a solution. So y of t is equal to. Now we just have to do the transformation, right? I guess getting a little anxious here. We should make sure that we know what we're transforming back. So the derivative transform, right? We see that this is a first derivative of something. So this transforms back to f t times f of t, t to the first times f of t. Yeah. Oh, yeah. So what happens there? So we'll make this into a positive and then this into a positive. Yeah. So there's a -1 here, right? To the first power. So we want this to be -1 here also, which makes this to be a positive 1/2. Right? And so the positive 1/2. Remember that this factor that I want to multiply this by would just make this expression look exactly like this s that I have. And so, I wish you would have gotten this earlier instead of doing it now. But thanks for catching it. Yeah, so I hope that didn't confuse too many things. That there's a -1 that goes on the outside of this because of the formula. It's -1 to the n to the first power, our first derivative. And so that made this positive 1/2. And now the question I had was if I backtrack to my earlier question, what do I need to multiply this by to get s over s squared plus 9 quantity squared? And since this would have been a positive 1/2, then I would have just had to multiply by positive 2. So that's why that's positive. All right. So now I'm looking at the transform of s or of f of s, where f of s is actually equal to this function right here. Um, so, oh man, oh, this is an s. So this is a cosine, right? So this transforms back into f of t, where f of t is a cosine. So that was the derivative that I was looking for. This is the derivative that comes from this function, which is a cosine transformed back. So now let's see if we can write it out. So there's a 2 that I have out here, and this whole thing in the brackets will become t to the first power times f of t cosine 3t. What? Because of this. Oh, it's this thing. Crap. Maybe the convolution was easier. All right. All right. Sorry, guys. I'm jumping the gun a little bit. Let's see if we can backtrack a little bit. I wasn't quite finished with this thought. That's why I was kind of rushing. So let's see if we can write this out a little bit better. We have f of s is actually equal to this thing in here. Um, oh, we need another constant. Yeah. So we need an extra 3 in here, right? Crap. All right. Man, let's try that again. All right, so let's go back to this idea of we want to take the inverse transform of s over s squared plus 9 quantity squared. Okay. So we want to take the inverse transform of that. And for us to do this, what we need to do is we need to identify this as the inverse transform of, now according to the formula, this, if we find the inverse transform of -1 to the n, dn over ds squared of some function, f of s. What? Oh, n. Yeah. Yeah. This is, which one is this? This is that first one. It's this one. Yeah. Well, we can use it. And the example that we did was using it to go into the Laplace world. The other way to use it is to bring it back to the real world. Right, right. And so if you have a feeling, that your function looks like a derivative of something, then maybe we can take advantage of this inverse Laplace. And that's what we're trying to do. Well, if it does have the derivative, then it will work. You know, if we know it's a derivative, and constants can always just be moved around. And so I think that's the issue that we're having, is playing around with a constant. So it can uh, it can work. It will work, except we just have to be tricky with the constants. Right. Yeah. So we have to try to see. So let's see. Um, and this is equal to, according to what we have, it's the inverse Laplace of. So let's put all these things together. We have 1 over s squared plus 9, 3, I think, right? So we want a 3 here, but then we've got alpha to be 1/2. So it's -1 to the first power, and then we have a -1/2, and then the dds. So there's an extra 3 that comes out. So we have to divide out by that extra 3. Unfortunately, the Laplace transform and derivatives and integrals are all linear, so any constants that we come up with, we can always pull outside. So we insert a 3 in the numerator, which means we have to divide a 3 in our term, and then we have a derivative. So now, does it look like it's okay? So the negative goes away. Oh, that extra 2 that comes out, we should put a 2 up on top too, right? The 1 over 2 here, but then we need an extra 2 that comes out. Right. But then because there is a 1 over 2 that comes out, we need that 2 there.
So I think according to Chain rule, we'll take the derivative of the expression. There's gonna be a 2
There's going to be a 2.
because of the
So there should be a 2 here, or no? There's a 2 that comes out, right? And so we don't need this. Okay. All right. Whew, man. So according to this, our solution should just be t to the first power, because n is equal to 1. So t to the first power times f of t, where f of t is the inverse transform of this function. So there's an extra 1 over 6 over there. So this is the function that we're looking at, and then there's an extra 1, there's a 1/3 and a 1/2. So then that transformation is going to bring it to 1 over 6. And then this is a sine or a cosine? Sine of 3t times t. Oh, because of the k squared plus 3 squared? Because it's only a first derivative. This s over s squared plus 9 squared is only a first derivative of this. All right. Well, let's just write the answer. So according to our solution, when we do the Laplace transform, we're down here now. Y of t is equal to, and there's a 1/6 here, t sine 3t. So that's the first part. The second part is 2 what? 2 cosine 3t, and then the last one, is it a plus also? Plus 5/3 sine 3t. Man. So I encourage you to do the convolution way at home. I think now we would actually see that it's easier because it's easier to identify. It's easier to identify the product than it is to look at it as a derivative of something. And when so the difficult part would be actually doing that integral. Maybe we should do it. Yeah, why don't we do it? Let's do the convolution. Star. Who's counting? All right. So if we want the inverse transform of this, the inverse transform of this is a product. So the inverse transform of a product would be a convolution. So this would be equal to f convolution g, where f would be the transform of this. And then now we need to generate those things again, those constants. So we need a 3 here, so we get a 1/3 out. So we have s over s squared plus 9. That's cosine 3t times, and then we have a 3 over s squared plus 9. That's sine 3t. And then there's a 1/3 out. So it's a 1/3 cosine 3t and then convolution sine 3t. So what is the, uh-oh, I'm out of room here. So it's a 1/3 integral from 0 to t of one of the functions, cosine 3t, or tau. We'll have to use the tau, times sine 3t minus tau. So the thing to do is that to realize that there's some big identities that allow you to solve for this. Is it okay if I just use the the sign of a plus b or a minus b or whatever, which are some trig identities that it's a little big. So there's some trig identities that I don't have memorized, so I'm just going to ask Wolfram to calculate this for me. So Wolfram, Let's see how this will do. So integrate. I want to integrate the 1/3. Let's keep everything there. 1/3 times cosine 3x times sine 3 t minus x dx. So our x is going to be our variable. We're going to go from 0 to t. See if that can't integrate. Why can't I integrate that? No, it shouldn't be. All right, let's see. 1/3, I think, integrate. No, I need limits. I'll just integrate. Oh, I have an extra parentheses. Damn it. There's a 1/6 and everything, right? Oh, okay, good. Well, if you use Wolfram, right, it'll be a lot easier. All right. So our big problem for next time is called the Dirac delta function. Oh, there's a quiz for you. The take-home quiz. So I forgot to give you. I should have given you a quiz on series, and I feel like you should. I want to see your progress on doing series. So there's a problem online in Canvas that's due on Monday, and so I want you to have that printed, written out on a piece of paper, and submitted to me on Monday. Tuesday, whatever. So also on Tuesdays, if you're gonna do a makeup test, you should have that turned in also, because I'm not gonna collect it after class. I want it in class. I'll collect it, and then that's it. Okay, yeah, I'll do that too. The idea is that I should have the thing from Rance, and so. But if you have the card, you should keep it just in case.